As we discussed in the previous unit, in order to make software easier to change and evolve, we have to write our applications so that dependencies of one type on another are eliminated or minimized. Hence, we've talked about the distinction between essential and inessential coupling. Essential coupling results from the dependencies that exist in the real world. For example, if a bank account has an owner, that dependency has to exist in the application. Inessential coupling comes from the way we build applications. Whether we make the account class depend on the owner class, or we use an interface so the account class depends on the necessary behavior such as assigning an owner or changing an owner. These result in inessential coupling because they have nothing to do with the real-world dependencies, but come about from the way we have to build software applications using programming languages. Design patterns allow us to minimize the connections caused by both essential and inessential coupling. In the code example in the previous unit, we saw a simple example where we used interfaces and the factory design pattern to minimize the coupling between the customer class and the customer manager class. This relationship did not exist in the real world. The customer manager class only exists to isolate customer functionality from how customers are stored and retrieved. Design patterns can also be used to minimize the changes needed when you modify essential coupling. Interface design patterns, refactoring, and similar techniques are part of the logical design of software. But in order to get the maximum benefit from our logical design, we have to pay attention to the physical design of the application as well. Integrated circuit designers realized this a long time ago when they pay attention not only to the way they design the logic of a chip, but how it's actually physically implemented in silicon. So we have to do the same thing in software. Software designers have to pay attention to how their code is arranged in assemblies and how these assemblies are versioned. So software is written with a logical design in mind, but is implemented through a deployment process. The fundamental idea of physical design is to group your classes into assemblies to minimize the dependencies among the assemblies with as little associated performance degradation as possible. And when you pay attention to physical design, you get several benefits. It facilitates the division of an application among different programming groups because you can assign different assemblies to different programming groups. At the same time, it provides the ability you to put unit tests around these assemblies so that when you partition this among different groups, when they release to other groups, you can be pretty well assured that these assemblies will function properly. So this aids parallel development. It also makes deployment easier because it minimizes the amount of physical change you have to make on the server or on the client machine when you upgrade. It's easier to create and test emergency fixes, whether you're in a desktop or web environment, because you have a smaller unit that you are deploying. So, what are the basic concepts of assembly partitioning or physical design? What we have to do is look for the fault lines in the application, where the application naturally divides. And there are two key concepts here, or two sort of signs that you look for. We should treat interfaces as fundamental types, and that will give us one clue as how to partition this software. And we should also look at our design patterns to indicate where the application naturally partitions. So what does it mean when we want to treat interfaces as fundamental types? Well, we talked about in the previous unit how interfaces actually can be treated as primitive data structures. We create dependencies on behavior instead of the implementation class, and by creating this dependency on the behavior, as we discussed previously, software becomes easier to change. So if we treat these interfaces as fundamental, they naturally go in separate assemblies. So in our particular case, the iCustomer interface and the iCustomer Manager would go in a types assembly. Now, how many types assemblies you have actually depends on the nature of your application and the patterns of your application. We can't come up with a general fixed rule, but the idea is place these types in the appropriate groupings in separate assemblies. At the same time, the implementation that goes behind these interfaces naturally falls into separate assemblies themselves. So the first thing to look for is how the interfaces as fundamental types cause a natural partitioning of your application. Another way to look at how your application should be partitioned into assemblies is look at the patterns that we use. If you look at a pattern, and we had one example so far, the factory pattern, you can look at the pattern from 3 points of view. There's the code that implements the pattern, the code that implements the factory pattern, the code that uses the pattern, in our case, the main application, and the code that the pattern isolates from. And this indicates possible assembly partitioning. So we have the application that we would put in one assembly. The customer manager factory might go in another assembly. And the customer manager itself might go in another assembly. Now, whether you actually do this or not, again, depends on your actual application. In this particular case, we've put them in separate assemblies to illustrate the point. But again, you have to use the appropriate judgment, because as we discussed later, there is a downside to having too many assemblies. Now, ideally, each assembly should have a strong name which allows the assemblies to be versioned and therefore have a unique identity. And with unique identities, then you can deterministically install and uninstall parts of your application, because you can have a bill of materials for each application and you'll know exactly what's there. And if you wish, you can use application and publish a policy to declare version compatibility. Nonetheless, this is not absolutely required. And everything we discuss here works well even if you do not use strong names. When you divide your application into assemblies based on the appropriate logical design characteristics, we can then evolve these assemblies independent of each other. This introduces the idea of viewing assemblies or groups of assemblies as components that can be compiled and tested together. They can be versioned together as well. But the important thing to realize is that what we are trying to get to here is partitioning to allow these assemblies to evolve independently, or these groups of assemblies to evolve independently. Reuse may emerge, but it's not the goal. Reuse in a real way is very difficult to achieve and only comes with a great deal of experience over time. The other thing that physical design enables is design for testability. When you think about the interaction between your logical design and your physical design, you can begin to see how this can make your application easier to test. We discussed using the factory pattern to partition the main program from the customer manager functionality. By using this partitioning to create separate assemblies, it allows both the main program and the customer manager classes to be tested and deployed independently. Well, it's easy to see how the customer manager class can be tested independently by creating a test program that creates instances of it and tests its methods, and similarly with the customer code. It's a little more difficult to see how the factory patterns allows for independent testing of the main program. In a subsequent unit, we'll talk about dependency injection to demonstrate how this could be done. For the moment, let's just note that dependency injection would allow us to return an interface from the factory that implements an I customer manager implementation that might be different from the one that we actually use in the actual application. And the reason for doing this is that suppose the real customer manager functionality uses a web service that's not always available or costs money to use, or it's too time consuming for frequent unit testing, because remember, when you run your unit tests, you want them to run relatively quickly, so you get into the habit of running the unit tests every time you check in code or before you check in code. Returning a stub or a mock object would allow us to independently test the main class. So you can also think about how you partition your application to make testability easier. Now, nothing comes for free in life, and certainly this is true of software. Too many assemblies in an application can be very problematic, because if you have many assemblies, you have to manage them, and that can be a nightmare in itself. So clearly, you don't want to put every class in every interface in a separate assembly. You have to think about what the probability of change is and group things together that would have the tendency to change together. So then you can version these things together and deploy them together. With better physical design, it becomes clearer what versions of the software developers are working against. If you do change assembly versions, you should increase the version number of a change assembly before deploying it to QA or test. That way, when QA reports a bug, it's a different version number than the one development is working on, so that you can be clear about which version the bug is reported against. And if you put things in separate assemblies, you can actually have reduced encapsulation, because things that would be marked, methods that would be marked as internal, have to be marked public. And too many fine-grained assemblies means too much has to be deployed when you make a small change to your application. And of course, loading assembly produces performance problems. So you have to analyze the performance patterns of your application. Do all assemblies load up at once? Or is the load distributed over the lifetime of your application? Does it matter to the users? Is this a UI-intensive app? Some users are willing to tolerate a little longer startup time if they're going to spend 10 minutes to an hour with the app. Other times you want the quickest startup time. More assemblies does increase the working set of an application. Does that matter? Depends on your application. The problem, of course, with all performance statements is you can always conceive a set of circumstances where they might be true or false. You have to look at the actual application patterns of your particular application. So in summary, good physical design facilitates the development of a software application by multiple teams. It also increases the testability of an application, and it becomes much easier to enhance and to test parts of the application independent of each other. Noticing what are the fundamental types and what are the important design patterns used will help you decide how you partition your logical design into its physical assemblies. And we will see the power of this physical design as we evolve our assemblies in subsequent units.